Okay, let's get going here. So it is the 9th, correct me if I'm wrong. I had the 8th on the slide. Here's what we're going to talk about today. We're going to start with, maybe you guys heard about this. I already talked to a couple people about it. It actually is this thing called the Heartbleed Bug. And it relates exactly to what we talked about on Monday as far as cybersecurity goes and about the security of the World Wide Web and cryptography and all that. So I just thought we'd spend a couple minutes just kind of talking about what happened and what the big deal is with it. And it is actually a pretty big deal. Then I'm going to talk about the final assignment, which we will have out today. Bruce and I have been working hard to make sure it's all put together. And we'll talk a little bit about that. And then one of the data structures that you may want to use, actually it's an abstract data type, but one of the structures that you may want to use is called a set, which we didn't explicitly talk about. And so I'll just mention a few words about that. And we didn't actually build them, but they're fairly straightforward. So you may want to use that for your final project, for part of your final project, maybe not. And then we'll talk about this new idea that we haven't gotten into yet called graphs. And they are possibly not what you think about when you hear the word graph. So we'll get into that. Okay, questions before I begin? No? All right. So the Heartbleed bug. So yesterday, or I guess 2 days ago at this point, somebody realized that one of the main security communication protocols for the World Wide Web actually had a big bug in it. In fact, it undoes web encryption, basically, right? And it's kind of a nasty bug. What it is so when your computer, and I don't know all the details about this, but when your computers are talking together over secure connection, okay, there's this little function called a heartbeat function, which basically it kind of every so often pulls the other computer for some data, right? Like kind of at a very kind of high level. It pulls the other computer for some data, and then this is all over an encrypted connection. But then when it gets the data, it actually stores the data in memory somewhere. Well, it turns out that they always store a fixed amount of memory, even if you only send like 1 byte back. So and at least they say they store that. But what they do is they basically have a pointer that you have access to an entire like 64 kilobytes of space in your computer if you are the person asking for sending that little data around. Bottom line is the bug, which affects like 2/3 of the computer systems in the world, is not secure anymore. Right now, you can upgrade it. In fact, probably over the last couple of days, like every system administrator in the whole country the whole world has probably been like furiously upgrading this thing because they have fixed the bug. But in the meantime, if you didn't fix it, then you can end up compromised, like your passwords and other things all compromised. In fact, let's see, I looked it up there was a big discussion about it on Reddit, right? Why do you guys laugh every time? Am I too old for Reddit? Is that what? I don't know. Anyway, so this is what the first post is. It says, this may be the biggest security vulnerability of all time. Now, hyperbole aside, that may or may not be true. But basically, this is what it says. It says, allows you to connect to any server running OpenSSL and steal anything in process memory. That's that little extra 64 kilobyte memory area. And your keys might be there, other information you don't want leaked, and so forth, right? Let's see. There were a couple other interesting comments about this down here. Nope. And nope. By the way, this one was don't go like trying to see if computers are vulnerable, because some countries will get arrested for that, by the way. Anyway, let's see. Here it explains it pretty well. In brief, there's a heartbeat mechanism. It allows the client to say, here's n bytes of data. Please give it back to me. And then it sends it back. But basically what it's saying is you'll ask for 1 byte, and it'll give you 64 kilobytes back. So, and whatever happens to be in your memory at the time. So not such a good thing. So all the stuff we talked about, like with web security and encryption and all that, people are still having problems with it and still like having bugs that don't get fixed. And by the way, OpenSSL, which is what most of these web servers are using, is a completely open function or open source program that people have been able to look at over time, and they have been able to say, you know, they've been able to debug it, but I guess this little bug got missed somehow. So not so great. Okay. Questions on that? If you notice extra like charges on your credit card, maybe it's because of this. Watch out. All right. So the next thing I wanted to talk about was the song search, which I mentioned the other day. This is our next project, and this is actually a project that's been given a couple of other times in Comp 15, and I think you'll find it interesting. It is going to take a bit of coding. Like it's not like a trivial problem at all. But what it is you're basically going to be, we are going to give you this database of songs, lyrics basically. And the database has 172,000 songs in it, which is a lot. And it's about 200 megabytes, which for the types of things we've been dealing with, that's like enormous, right? In the grand scheme of things, yes, you have gigabytes of memory, but like each one of you when you're running this is going to use at least 200 megabytes of data if you're going to store this, well, depending how you store it, but you're going to be using this. So it's 200 megabytes of data, meaning that when you're doing your search, right, you'd better have a good data structure or a set of data structures. Because if you don't, you're not going to actually, it's not actually going to work. Like it's going to be so slow you won't even be able to tell that it's working, right? So efficiency is going to be key to this, right? We've talked about some very efficient data structures, right? I do not think you would be wise to use a linked list for this, right? It's just not going to be smart, right? Think hash tables, think maybe binary trees, something like that. At least you're getting logarithmic or better behavior. Okay, hash tables is great for this sort of thing, but there's a couple different levels that we have to kind of go through. The assignment's going to have two parts, okay? And it doesn't mean you can work on them separately, but the first part is going to be you have to come up with some design document that says, here's my plan, okay? And this is going to kind of force you over the next week to think about this and to think about it in enough detail so that you can actually go and start coding it. You are completely welcome to start coding it now, but before you actually before next week, you have to see a TA or me or Bruce or somebody and talk about and get it signed off that you've talked about your project. In fact, I'll put something in there that says, who have you talked to about this? Okay, you have to get it, you have to go discuss it and lay out your plan for how you're actually going to do this, because there are definitely some tricky parts to it that you'll need to kind of think through before you go and code. So that's going to be next Wednesday, that's going to be due. The following Wednesday, the program itself is going to be due. Okay, so I think that's 2 weeks. And it should be enough time, especially if you start thinking about it now. Okay? Questions on that part of it? All right, so here's how it's going to work. Okay? Here's how it's going to, in fact, I'll show you an actual run here. You are going to be able to, type song search and then this lyrics database. This is the 200 megabyte long one, or sized file. And there's also we're going to give you some other much more scaled down databases too, so that you can use those for your testing. And then you're going to type in a search word, and notice something about this. There's no like prompts or anything, right? It doesn't say, what word do you want to search for and so forth. That will be handled on a web interface if you're not using the command line interface. You're going to have two ways to run this. One's going to be a web interface that you actually run your program and it sets up, it kind of runs continuously waiting for input from the web server or the web interface that Bruce has written. And you'll be able to type in your search term there. Or you'll be able to run it to debug on the command line. So anyway, you run it and it starts listing and it goes through and it finds where that lyric is. So Boston, right? So it turns out that in Kenny Chesney's song, called Boston. She comes from Boston, and this is the word that it actually picked up. Now, notice something about this word. What's different about this one than about this one? Capitalization. Okay, so we're going to have to figure out a way to deal with searching for words that aren't capitalized. Okay, maybe we'll talk a little bit about that. In fact, I'd be happy to answer any kinds of overall questions about that stuff. But we are going to give you a C++ function that reads in the file basically word by word. And what you'll have is the artist, the title of the song, and then the next word in the song. And then you'll pass that on to your other function and then deal with it. And however you want to deal with it in terms of getting it into your database, you can do that. It will be, the word you get will be like uppercase Boston with the little comma there. By the way, that's the other thing, right? There's uppercase Boston, but it's also got a comma. So you will get that whole word, Boston and comma, and you have to figure out how to just search for Boston in that, right? What we're not talking about is if you searched for ton, T-O-N, it would pick up that, right? That is not what we're talking about. Okay, that is not considered a word. The word is going to be anything that's on one side or the other has white space, or is the first word in a song. Yeah, Eliza.
Can I search for title or artist?
We're not going to have title or artist for this one. No. Well, no. This one, this is Boston. It happens to be picking up from this line here. Okay. So in other words, it just happens to be the title Boston. But in this case, it's going to pick up the context here. So another thing you're going to have to be able to do is print out the context. In other words, if you search for the word Boston, it can't just say, hey, it's in Boston, the song Boston by Kenny Chesney. It's got to say, here are the words that come before your word that you searched for and the ones that come after it. If you happen to search for the first or second word in a song, well, you're only going to print the first two words. You're not going to print anything before that. You're just going to print that song. So if you searched for, let's say she was the first line of the whole song. Anybody know that song? Yeah, is that the first word of the whole song? I don't know. But if it was, then you would print out the, in fact, are you sure? It might be, actually. It might be, because the reason is because I actually had, normally what we're going to do is we're going to have it say the previous 5 words. And I actually wrote this program to do this already. It's only printing out the first 3. So I believe this might be the first sentence in the whole song. Anyway, and then it's going to list a bunch, and you're going to limit it to the top 10 songs that meet this requirement. Okay? In other words, the top 10 songs ranked by how many times that word shows up in the song. Okay? So if Boston happens to show up a lot in the song Boston by Kenny Chesney, I guess. Anyway, so that's it. I'm going to show you another example. Yeah?
Is it only searching for a word, or can you search for a phrase?
We're just doing a word right now. Searching for a phrase would be in kind of another order of magnitude harder, but that's not to say you can't modify it at some point to do that. We just won't be testing that. Yeah?
What do you mean by the top 10 frequency? So you'll have to know how many times that word comes up?
You'll have to know how many times that word comes up in the song. Yep. Now you have to figure out how to store that information in your database, such that it's fast, such that it's searchable, like that. Yeah, Kuyen?
What if they are ties?
Yeah, if they're ties, we're not going to worry about the order. So if you come up with 2 that happen to have 10, or like let's say 2 songs happen to be 22 times, the word Boston is 22 times each, you print out one before the other, we're not going to worry about that. We're going to figure that part out. Yeah?
What if you have like 10 and 11 are tied or something?
Same thing. It doesn't matter. If there's 10 and 11 tied, then you print one and not the other. It's fine. Yep. I don't think we're not going to limit that one. Yeah, Rose.
With this result, it looks like you're printing the same song twice.
Yes. Well, let's take a look. So this line in the song says she comes from Boston, works at a jewelry store. Some other line in the song says while they're talking, she's from Boston. That's a totally different line in the same song. So therefore, you have to print both times it shows up. You have to print all the times it shows up in a song. For all top 10 songs. So you could have, it might show up, Boston might show up 40 times in this song. You're going to print 40 times of this one, and then 30 times for the next song, and 22 times for the next song, and for 10 songs. That makes sense, Bruce? That's where we're going with it. Yep. Question?
So we have more than 10 results.
Right. You will probably have more than 10 results, depending on what you search for. I'm going to show you another, like a real run in a second, and we'll see. Yeah.
Why does Boston show? I mean, I get that that's like the next lyric, but are you supposed to have Boston come twice?
In this one, it does. This one, yeah. Now, it may be that Boston's like the second word and the fourth word in the same sentence, so the context will overlap. That's fine, too. But for every time you find a word in the song, you're going to find the previous 5 words, next 5 words if they exist, print it all out, and then the next iteration of that same word, same thing. Okay? These are the kinds of things, this is again why we want you to have this design document, because you kind of got to think about all these things before you like launch into it. Okay? Yes?
So theoretically, the next part of this song would say title Boston, or and then it would say like from Boston, she comes from Boston.
No, I'll show you the. Well, actually, it's. I guess I don't. I guess I could show you the actual song list, but in the document we'll get that it'll lay out what the format is. Basically, song title, or maybe it's artist first, then the title, in a format that we will read in for you, and then the whole lyrics, right, of the song, and then the next song, a break, and then the next song.
Yeah, but like in this list when you run it,
Uh-huh.
if you're gonna pull
Yes, I believe. I'm not sure I quite understand exactly what you mean, but yeah, it's going to say it exactly this. It's going to say title, Boston, artist, Kenny Chesney, the context. Then the next time the word's thing, same thing. It's going to say title, artist, etc. Okay? Yeah, question?
I was wondering, for the second one, since Boston's in there twice, would there be, like, is the second one for which Boston is that for? Because it's twice.
Oh, okay. So sorry, I probably should have chosen a different example for this. The title is irrelevant. You are not searching.
Not the title. It's in the context. In the context of the second one, Boston appears.
While they're talking, she's from Boston. She comes from Boston. Oh, you're right. It's going to pick the first one and then do the 5 words here and the 5 next words. And if Boston happens to be the next 5 words, that's fine. And then it's going to do the next, and I don't have the rest of the search here, but the next one would probably be this Boston with the previous 5 words and the next 5 words. You see? So yeah. Okay. This is kind of a fun project, I think. Let me see if there's anything else here. Yeah. Let me actually show you it running. So because the database is pretty big, I just did the search with Boston here. Because the database is really big, it will take a while for your program to read it in, the whole thing in. I wrote the little program, actually I just knocked it out in Python yesterday, and this takes about 3 minutes to read in the file and process it, right? And that's like, best I could do in 24 hours, right? I haven't written in C. It might take a couple minutes if you do it effectively. But what it's going to do, for every search, you are not going to read the database every time. Right? You're going to read the database once and then take a whole number of searches. Does that make sense? So you're going to keep searching on the database already in memory, and I'll show you how fast this one is. Somebody want to give me a word? By the way, this don't be alarmed if you see like naughty words in here. It's like a lot of lyrics. Anyway, anyone want to give me a word? Not a naughty word? Chris. Okay. Chris. All right. Boom. There we go. Okay. So actually, I'll just go to the top of the list here. Oops. Chris. There we go. Okay. So you saw how fast that search was, by the way. 200 million songs, and it went like that because the data structures I used made it efficient, right? So there, it's a lot of, I don't know. All right. Yeah, I mean, look, everything is in here. Like, nobody's like gone through this and people have cleaned it up to be that, but that's it, right? So again, it says the title, the artist context, et cetera, et cetera. Okay? All right, anything else?
Austin.
What is it?
A-U-S-T-I-N.
Hang on, we'll do it this way. There we go. Lots of stuff in Austin. Something in Blake Shelton, right? Okay. So on and so on and so on. Japanese meets Chinese in the USA. I don't know what that is. Electric eel shock. Right? So you'll get lots of interesting, some Tupac in there. You'll get some interesting lyrics in there. And I think the database at this point is a few years old, so you probably won't find your latest and greatest. And I was planning on like scrubbing all Miley Cyrus from it, but haven't done that yet. All right. Actually, let's see. Miley. I don't know. It won't search by thing, but Billy. Right there we go. So and by the way, some of this is not cleaned up either. I think the database comes from like people typing in like the lyrics, like I think that's where it came from. So people might have typed in something in the wrong place and whatever, and that's that. Okay. Any other questions? If you don't find a match, A, B, C, D, E, F, G, H, I, J, right? It'll just say end of report, no match. Okay. You can search for like A, and now that's going to take a while, probably because there's a million A's and a lot of A's in there, right? That was probably not a good idea. But there it goes. That was that took a few seconds, right? So anyway, and then you look up here and. Whoops, I missed it. Hang on, there we go. Yeah, so who knows, right? It's like some other, it's probably some other language or something, who knows. But anyway, lots and lots of lyrics in here. You'll have fun playing around with that part of it, okay? What you don't need to do is copy this huge file into your own personal directory. I've showed you how to do it, what's what we call a soft link to it, which means it will seem like it's in your home or your directory, but you'll actually be using the one that's in the class web or the class pages directory. Okay. All right. Let's see. What else can I tell you about this? We're going to give you the code to actually read in the database, but it's kind of sparse. I mean, like I said, it will give you the title, the artist, and the next word in the song, and you have to figure out how to process that. That part's going to take a little bit of coding as well. And then punctuation we talked about, and then context, previous 5 words, next 5 words. Okay. All right, and then this is not trivial. you should definitely test it on the smaller data to make sure it's working. When I was trying it last night on the giant database, I mean, like, I'd make some change, and then 3 minutes later, I'd get to test it again, because it would just sit there and chug away until it does it, right? Good engine, takes a minute or two to read. Bad engine, forever. Okay, so that's why you want to test it on small data, too. And you want to kind of make sure that it's, once you test it on big data, you'll very quickly find out if you've got bad data structures. But make it work with the small data first. Okay. Questions on that? Any other questions? Like I said, I'll try to get the document out this afternoon, early this afternoon if I can. And we'll go with it there. Let's see. A couple more details. We talked about ranking the songs. You'll be able to run it from a web-based or the thing. You can use whatever classes you want. Okay, you can use, if you want to use, you can't use like song search database class, right? But you can use the standard library classes. So there happens to be a class called map, which is kind of like a hash table. It's very similar. I believe the map that C++ uses is based on a different type of binary tree called a red-black tree that we haven't talked about in our class. It might not be as fast as a hash table. We have given you a code to a very good hash function to hash strings if you'd like. So you can build your own hash table. Just be aware that you will probably need to increase its size, right? Make it grow. And you can use other things too, like sets and vectors. And we'll talk about sets here in a sec. Okay. All right, so actually, let's get any other like overview kind of comments on that or questions? Okay. Sets. So you might want to use this thing called a set. I'm not telling you should. I'm not telling you have to. But people, I guess, in the past have. And we hadn't actually gone over sets. There is it's a relatively straightforward way to use a set. What a set is it says, here's your items. Like, I'm going to take an item, and I'm going to put it in this set. And it's just like math sets, right? If I take the same item or one that's has the same properties and also put it in the set, then the set will not hold 2 copies of those. It will only hold 1 copy of it, right? So for instance, you might want to have a set of, let's say, songs, right? And so you have a word that says, what songs do I have I found this word in? And if you find it in 10 different songs, you don't want to store 10 different song objects. You want to store like 1 song object. So you might want to have a set that's based on you just keep throwing the same song in there, and it figures out the details and says, oh, I've seen this song already. No worries. Okay? There are a couple caveats to using this that I actually didn't put on the next slide, but you can insert any object into a set, but you have to be able to compare 2 objects. So you have to do a little comparison operator. I would be happy to show you how to do that. There are lots of places online that it shows you how to do a comparison operator. But basically, it's going to say, is this set the same as this other set? And you have to be able to compare them, right? And that's it. And so that's how it knows whether to put it in again. That's all. That's the details there. Okay. Let's see. You might want to consider using a set as the value to store the hash table. Like the key is the word, and the value could be a set of songs, something like that. Just trying to get you thinking. Okay. Let's see. Here's the example that I had, and we don't need to go through this right now. Just it's on the website, so you can grab the code. I did not implement. I implemented it for strings, which already have the ability to be compared. If I did it for a struct, you would have to do that comparison. And in fact, if someone reminds me, I'll actually write up a little one where it shows the comparison. But in this case, all it's doing here is it's setting up a set, and then it's saying it's going to insert a string, and then it's going to insert a second string, and then it's going to go insert a string again. And what actually prints out is, I don't have the printout here, but it's going to print out the fact that the first time you insert a string, it's got 1 item, and then you print out another, and then you insert a second string, and it's got 2 items, and then you go and insert a string again, and it's still got 2 items. That's the whole point. Okay, it does not get reinserted. It says, oh, it's already there. Yeah, Walter. It does not know there's 2 of a string. It just says a string is in the set. That's all it knows. Yep. Okay. So if you can think of a way to use this, great. If you can't, you can probably come up with a different way to store store your songs or whatever. I thought I'd show you this just in case you wanted to use it and you hadn't seen it before. Yeah.
What's the type of word result?
In this case, so yeah, this word result is actually an iterator, which is a C++ thing which says it will give you back the actual. It will not give you back the word because you actually searched for it, right? But it will give you back. It'll tell you whether or not it was found in the set. Like that's the first thing. And if you get an iterator, you can actually walk through the various values once you get that. Not in this case. In the find, this is just saying, did I find it in the set or not? And that's kind of an important one. Okay. And you can figure out which one it is by getting that, but it's you can get an iterator of all of them as well, and then walk through them all. They are not in any particular order that you the order is based on the comparison. So however you're comparing them, that's the order they end up going in. Okay, in general. All right, that's sets. If you have more questions about that, feel free to stop by at office hours and do that. Okay. All right. Other questions on sets or the homework assignment that's coming up? Okay. I hope you guys have fun with it. It should be a fun one. So the next thing we're going to start talking about are these things called graphs. Okay, we're talking about what the computer science or mathematical type graph, not like a graph of data, right, or a chart or something like that. That is not what we're talking about over there. We're talking about shoot, my laser pointer's dead. We are talking about the first one, which you may have seen before, and in fact, it is a node-based structure. Okay, it's a node-based structure, and it looks a lot like a tree, except like goofed around, right? It's not in a nice order, right? Like our tree-based structures are, and that means that we're going to have to deal with it a little bit differently. Okay, but that's what we're going to be talking about. So let's go through some details about what graphs are to begin with. It's a very general data structure. Okay, in fact, it's actually really common in computer science. Once you kind of get to the next level, you use graphs for a lot of different types of algorithms. Okay, it happens to model some data very, very well in lots of different ways. Okay, it is nonlinear, of course, and it consists of nodes and links, but doesn't have that underlying structure that a tree does. Okay, so you have to deal with it a little bit differently. Okay, you have to deal with it in a way that you can still get to all the nodes, but you have to store the information in a way that's efficient and also allows you to get to all the nodes in a known way. Okay. The simplest type of graph is called an undirected graph. That means that all these lines here, what we've got are, and I'll put up what these are on the next slide, right? There we go. These are called vertices. Singular, it's a vertex. Okay, and this is where you would like store some sort of data. Okay, well, you can actually store data in the edges as well. We'll get to that in a little bit too. But what it means to be undirected means that these lines do not have arrows on them. Okay, they are just connecting two vertices. Okay, an undirected graph has no directional decision between those two, between the two vertices that it's connecting. Okay, notice something about this. You don't have to have any order here at all, right? Like this one connects to this one, and this one connects to the other two around the side, and so forth, right? And it, let's see, hang on, see if I can. There we go. We generally label these as V sub something or other for the vertices, V0 through V, however many vertices you have, and then we label the edges as well. Not always, but sometimes we label the edges actually as well. Okay, because edge 0 goes between vertex 1 and vertex 2, or vertex 1 and vertex 2. Okay, edge 1 goes between vertex 1 and vertex 2. And so this is how we're going to actually get the structure for these graphs. Okay. All right. Questions so far? Yes, again.
How do you name something like edge between V1 and V4?
Between V1 and V4. There is no edge right now in this graph between V1 and V4. If you wanted to, you could put one in there and you just name it E5 or whatever it's left, E6, whatever the next one is. You could label it that way. Okay, and it's really completely up to you, or you will be given a graph that has them all labeled already. Okay, for what we're going to be doing with, we won't be changing the paths right now. We won't be changing the edges right now, at least for today anyway. Okay, all right. So far, so good. Okay. The structure of the graph also doesn't matter. These happen to represent the same graph, I think, unless I drew my or picked other things wrong. Yeah, Tara? Or Tara? Oh, did I do it wrong? Which one did I do wrong?
Well, on the left one, 2 and V3 are connected, but on the right one,
2 and V3 are connected. V2 and V3 are connected here.
no, it's not on the other one.
Oh, they're not on the other one. Sorry, you're right. Oops. Okay. I guess I gotta redo that one. Hang on. Let me just fix it right now. It should go from where to where? Let me see. It should go from. Hang on. I'm just. Let's see. V3 to V2. If I put one there, hang on. I put one there. That's what happens when you do this so late at night. Okay. So there to there should be edge 3. Okay, hold on. That one's edge 3. And then V3 to V4 did not exist. Right? That better? No. Why did I get this so wrong? I don't know why I got it wrong. The idea, that is bizarre. I'll fix it. I'll fix it later. I'll re-upload the thing. Apologize about that. Point is, you don't have to. You can modify the structure of what you see, but the edges and the vertices should stay the same if it's going to be the same graph. Apologize about that. Okay. Questions on that idea? Graph. The placement of vertices is not important unless you're doing this in the middle of the night, in which case it should be. You should make it the same. Okay. All right. So here's an example of how we might use an undirected, what we call a state graph. Okay, so we're going to use a graph to talk about kind of a little game here. Okay, we're going to show how you can use a graph to actually solve this game. Okay, here's the game. You have 3 coins. I don't know, anybody recognize this game at all? I'm just seeing the 3 coins up here. No. What it is you've got 3 coins, and one's heads, the one in the middle is tails, and the other one's heads. And you are trying to, through a series of flips, get to tails, heads, tails. Okay, so you're going to go from heads, tails, heads to tails, heads, tails through a series of flips based on a couple of very simple rules. Okay, and here's the rules. Right, the rules are you can flip the middle coin anytime you want. Okay, the middle coin can you flip back and forth anytime you want. You can flip an end coin only if the other 2 coins are the same as each other. Okay, so let's see if we can just do that. See if we can just get there. There's no other good chalk. Hang on. Let's try this piece to get somebody to give us some more chalk. Okay, I'll do it like this. Okay, it's going to be heads, tails, heads, and we can follow these rules to get to tails, heads, tails. Anybody want to tell me what they might do first? Actually, the only thing you can do. Right? You have to flip the middle because you can't do that. So then we've got heads, heads, heads. Then what? Which end? Doesn't matter. Flip 1, tails. Then what? Flip the middle, and that'll be tails. Flip which end? The right end. That'll be tails. Okay. And then flip the middle, and you got there. Okay, not a really particularly hard game, right? But that we could have made a couple choices in there. Okay, we could have made a couple choices in order to go one way or the other, but we went from there to there. Now, what you can do is you can use a graph. Now, if this was a much broader example, right, we would maybe want to use a graph to solve this sort of thing. But what we can do is we can construct what we call an undirected state graph, saying all of the different combinations, like describing all of the different combinations of moves that we can do. Okay? And this game happens to have 8 states. Why are there 8 states here? 8 different ways you can arrange those 3. What's that? 2 to the power 3, because each one can be either heads or tails, and you've got 3 of them. So it ends up being a combination of 2 to the power 3 or 8 different moves, right? And we call those states, actually. And we can go from head, 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 all the way to tail, 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 which is what we had to do in this little example. Okay, I don't believe there's any other way to do that. In fact, let's take a look. So here's the example of all of the different states. And I've actually put edges between the vertices. Now, the vertices in this case are like big, right? They hold the whole state, each state. And the vertices tell you how you can go from one state to the next. Is there a case where you can get to a state and you can't go backwards to the previous state? Remember our rules. You can flip the middle anytime, and you can only flip the ends if you're next to, if the other 2 are the same. Right? Are there any of these states where you can't go backwards? Let's just pick one. Let's say we went from this state to the bottom state there. So you've got tails, tails, heads, and to get to the bottom state, you're actually flipping the head to make it tails, tails, tails. In the bottom state, can you flip that tail back to be a head again? You can, because the other 2 are the same, right? So the reason this is an undirected graph is because you can actually go back and forth, and there's no wrong way to go in terms of you can always go back and forth to get there. Now, you can see from this in kind of a straightforward way, there's 2 different paths you can take, right? You can go up and to the left and around and back and to the middle, or you can go up and to the right and beyond, right? You have to first flip the middle one. You can't do anything else anyway. And then you got choices. We happen to pick the choice on the left, and then we did this, and then we kept going through the left path all the way up to the middle there. And you can screw up too, right? You can start going this way and end up down at the bottom, and then all of a sudden go back up that way and kind of go in this, circular thing all the way around. You can play this all day without ever getting to the middle, to the end condition. Okay, make sense? That's a graph, an example of an undirected state graph. Okay? And the lines are just the possible moves in both directions. Okay. Let's see, we can go between 2 states. Oh yeah, we have a winning path. Directed graphs, on the other hand, tell you which direction you can go from one vertex to the next. Okay, and you can only go that way. If you happened to, and I didn't draw I didn't put the vertice or the vertex or the edge labels on here. If you happen to start at this one in the middle here, and you go to this one on the left, well, you can never get back to the other one. Okay, in fact, there's no path to get back to the other one. Okay, you could start at the top one and then go around and then keep going around and go around and end up getting back at the top one. Okay, that means there's a cycle in this graph, right? But some you cannot get to, and some you can. Okay, and you can have edges that go between 2 in opposite directions. That's fine too. Okay, graphs is like a really big topic, and there's lots of different ways you can use these. But these are we're kind of getting the basics down here like this. Okay. Graphs can also have multiple edges. We will probably not talk about this much at all, right? They can have loops, which means you can have an edge going from one vertex to itself. Okay, that's actually a loop. Or you can have multiple edges in the same direction going between 2 different vertices. Okay? These are kind of a little more advanced kind of ideas. Probably won't get into too much of that. Okay, but you can do that. Just so you know. Okay. All right. How are we going to actually represent these graphs? Okay, I've labeled these graphs with just numbers instead of like V0 and V1 and all that to make it a little bit easier to understand here as far as this the way we represent these. One way we can represent them is this thing called an adjacency matrix. And the way you read this is the numbers on the left say, from 1, what do I go to in that direction? Like from 1, I don't go back to 1. I do go to 2, right? I do go to 3. I do go to 4. But then I don't go to 5, 6, or 7 from 1. So far, so good? Same thing with the other ones, right? If we picked 4, it only goes to 6 and 7 and 3. It actually goes 3, 6, and 7. right? 3, 6, and 7 in the chart over here, 3, 6, and 7. Okay. This is one way to do it. What's a problem with this method? Can you tell from the little adjacency matrix up there? What might be an issue with it? Yeah, Marcus. Yeah, as you get more and more nodes, it grows. In what case? There are 7 nodes here, and what does this two-dimensional table mean about the number in the table? 49 of them, right? So it's actually n squared representation in terms of space representation. That's one thing that's definitely an issue. Yeah?
You can't define multiple edges.
You can't do multiple edges. That's true. We're going to kind of limit ourselves to single edges in this case, but that's a good point. You can't do multiple edges, like if you were going 4 to 7 and then also again to 7 or something. You can't represent that. That's true. Although maybe you could say, instead of true and false, you could say the number of times you go there or something. I mean, you could modify this to some extent, right? But what do you notice in this case about the number of trues versus the number of falses? There's a lot fewer trues, right? There's many fewer trues than falses in this case. For most graphs, they are not connected that much between arbitrary nodes, right? You can have a fully connected one where everybody connects to everybody else, right? But you almost never see that. You see it in some very rare circumstances. Well, you see it in networking sometimes, right? When you have computer networks connected together. If you have a network where every computer connects directly to every other computer, it actually makes a very robust system, but it takes a huge amount of wires and coordination and so forth, right? So there are ways to do that, but many times we will have what we call sparse graphs, and you don't want to use that. You don't want to do this, right? Because notice on this one, like nobody goes back to 1. Nobody actually. You can't get to 1 from any of the other choices, right? So having that whole column there seems a little ridiculous. It's like wasting a bunch of space. Okay? Lots of wasted space, order n squared tables. How else could we do it? Any ideas? What a different way of organizing this would be? What do you think, Arkin?
What if we do a tree where you can then just, you can have the same, like 5 can appear different places, but 2 would only be connected to 5.
Oh, okay. So you could have a tree that's kind of connected to only it's the kind of children. That might work. That would probably limit it. Like all the falses would kind of disappear, right? It would be an odd-looking tree in some cases. I mean, it would be more or less a graph. But I mean, in terms of representing it, you'd have to figure out how to represent it, and I mean, in an array or something like that. But you could probably do that. Yeah, Tal?
What if you had a linked list where the number of connect pointers is equal to the number of...
Oh, yeah, that's not a bad idea at all, actually. So you have 1, and it's going to say, I'm 1, and then here's the ones I'm pointing to. Yeah, I like that. Okay, I like that. That's actually what we might do, right? We would have an adjacency list instead of an adjacency matrix, right? And what this is this just saying exactly that. It's saying just list all the vertices and then what each one of them, what it's actually connected to in the direction, and in the direction now, because these are directed graphs, right? So 1 goes to 2, 3, and 4, and nobody, if you notice, goes back to 1. And by the way, 6 doesn't ever actually doesn't have a directed edge to anybody from 6. Okay? So we can do this with adjacency lists, and it's much more compact because there's all that extra stuff that's not even in the chart, is in the graph is missing, or it's just not represented, which you don't need to. Okay? So many times when we're doing this, we'll try to do this in an adjacency list sort of fashion. Okay? All right. So we can store these with a hash table if you want also, right? You have the keys are the vertices, and the edges are the lists that you actually store in there. You can do that if you want, right? You have a hash table that hashes the key, and then it points to the list. Easy enough. Be pretty fast as well, especially for big graphs. And these graphs can get giant, by the way, depending on what your data set is. See these a lot. In fact, we'll talk about various times we would use these in real life too, what they can model. OK, guess what? You don't have to have just edges that go from one to the other without any extra information. You can have what we call a weighted graph. What that means is that there's some cost to get from one vertex to another. Right? So you have a cost that goes from vertex 1 to vertex 2, and that cost happens to be 2. Right? And from 2 to 5, that cost is going to be 10. Okay? So this gives you more information about this, the structure of the graph, and it gives you more information about what you like to deal with, and lots of cases have weighted paths here. Okay? Has anyone ever, let's see, what's a good way to phrase this? If you call on your phone, right, from, let's say, well, you guys all have, you don't have landlines anymore, but let's say you call on your cell phone, right, and your cell phone communicates at the speed of light in the sense of the signals going between your cell phone and the tower, right, that you're connected to. And then if you call somebody in California, do you know how the signal goes from Massachusetts to California? Any ideas? Sometimes it's a satellite. Most of the time it's not. Most of the time it's still these days actually a landline, and it goes through a number of switches across the country through a landline. And that is not necessarily at the speed of light, but it's very fast. Right? It has to go through a bunch of switches, and that takes a little bit of time, but it's very fast. Right? If it does go by satellite, right, it has to go from your cell phone to the tower, which is very close, to the satellite, which is how many miles away, on average, a communication satellite? Any idea? Let me start this way. The space shuttle is how far away generally? Well, now it's just on Earth, but the International Space Station. 200,000 kilometers. Space station is not that far away. Space station is much the 200,000 kilometers is on the order of how far away the moon is, basically. It's a little bit farther, but moon. So another guess? Yeah. 500 kilometers. That's about right. Yeah, it's about 200 miles, about 500 kilometers away. Okay, that's where the International Space Station is. Some of your communication satellites are doing that. But the problem with that is that if you're talking to a communication satellite, you guys have all seen movies where every 3 hours you get a sunrise, right? Because at the distance that the International Space Station or the space shuttle are going at, right? They go around and they go all the way around the world. And if you're pointed at it now, well, it's going to be moving, and then eventually it's going to go out of your range, right? Well, there's a different type of satellite called a geosynchronous satellite, right? Which will basically, they time it so that it takes 24 hours to go in its orbit, which means that as the Earth turns, and they put it kind of on the equator, right? So as the Earth goes around, it basically stays right where it is. Turns out physics dictates how far away that has to be. It's not 200 miles. It's actually about 22,000 miles. Okay, that's actually a pretty far distance. Okay, I believe it's 22,000 miles, 23,000 miles maybe. Okay, here's the issue with that. All this is leading to one thing, right? The time it takes for the signal to go from like the ground station here up to the satellite and back down to the other, like in California, is about a quarter of a second. Which means that, and that's at the speed of light, right? Which means that no matter what, you are going to, if you're talking to somebody in California and you are on a satellite link, you will have a quarter-second delay between when you speak and when they hear you, right? Laws of physics say that. That is an example of the cost of like the path, right? So if you're doing satellite-based communications, right, you need to get to the satellite and then get back, and that takes a quarter of a second. If you're doing land-based, you can actually do it much faster, and there's less of a delay. And so if you're talking to somebody from California and there's like lots of delay, you'll probably say, oh, my signal's bouncing off some satellite up in space, right? Which is kind of cool to begin with, but different story altogether. But it's not you know, you can generally tell. Okay? Anyone know how long it takes the signal to get from here to Mars, like for the Mars rover? Yeah, it's about 7 or 8 minutes. Yeah, 7 or 8 minutes, meaning that when we tell the Mars rover to do something, go left and check out that rock. 16 minutes later, or 14 to 16 minutes later, we get a response saying, okay, I'm going to turn left. Right? Like that's how long the delay is, just based on physics. So you have to, you know, if you're graphing these things, you have to kind of think about this. But anyway, the point is that we can have these weights on these edges, and going from one vertex to the next takes a certain amount of cost. And so let's say we were going from one, I think I might have this on the next one. Nope. going from vertex 1 to vertex 5. Okay, you can either go, you can go in a couple different paths, right? You can go 1 to 2 to 5, right? And that's going to take 12. The cost is going to be 12 for that, right? You just add these costs up, right? Or you could go 1 to 4 to 7 to 6 to 7 to 5, in which case it would be 5 plus 6 is 11. So it's actually, you go through more nodes in this, or more vertices here, and you actually have a, oh no, you can't go from 7. Sorry, wrong direction. Is that the only way you can get to 5? I think it is. Yeah, I guess it is. Let's pick a different one. How about 1 to 3? You can go either 4 straight there, or you can go 1 to 4 to 3, which takes a cost of 3, right? So there are differences in the cost. And these are part of the things we have to figure out how to calculate these for all the different types of graphs we're going to deal with. Okay, questions on that? Yes, Rose.
Why would you have a weighted?
Why would you have a weighted path? Well, like the example of the communication satellite, right? Sometimes you might have to, between two places, it might take more time to do something, or it might be more distance, right? Let's say you're driving from here to California, right? Well, depending on your route, right, the costs to go to different cities, you might calculate the cost in various ways, right? If you go, it might be slightly quicker, probably not from Boston to get to like San Diego. It might be less distance if you did it like a zigzaggy kind of way through side roads and things, right? So your cost in that case might be distance. But you also might, if you go, well, if I just get on 90 and go all the way west until I hit like Idaho and then go south, it's actually going to be faster. So your cost would be faster. So when you're talking about graphs like this, you do weights based on some parameter that you decide on.
So it's not something you want, it just
It sometimes happens, yeah. I mean, well, it depends what you mean by want. I mean, if you're designing something that's going to be based on various costs, sure. I mean, it's not that you want it, but it's the way it comes out in the data. Yeah, good. Okay. So here's this. You guys have all seen this. You're looking like the airline magazines or whatever, right? It's got your paths to fly from one place to another. Airlines don't fly between every city, right? If you want to go from here to San Diego, well, that's probably not a good example. Well, yeah, here to San Diego, there might not be direct, there might be. But many times there's not direct flights, right? They have hubs and things. And the airlines have kind of mapped all this out such that they minimize the cost in fuel, in time, in connections, and so forth, so that it looks like a big graph. That's really what it is. Okay, and the cost can also be, it can also be monetary, right? So you can graph it. So that's another example of the types of things we might want to graph. Okay, finding the shortest path from one vertex to the next, or the shortest time, or the shortest cost, or whatever. Okay, good. All right, so we kind of did this one already, right? 1 to 6, yes, we didn't do 1 to 6, but 1 to 6 is, from 1 to 4 to 6 is 9, or from 1 to 4 to 2 to 6, or from 1 to 4 to 7 to 6, right? And you can figure out what the minimum cost is. We're going to have to do some of this. Like there's algorithms, of course, to figure this out, which is what we'll get to either today or tomorrow, probably today. Okay, question, Walter.
So, how would you know that there is no direct connection from V4 to V1?
How do you know there's no connection going from V4 to V1? The graph is drawn that way. I mean, that's really it. You're given the data that fits this picture.
I mean, I thought this weighted path thing was like an alternative for the adjacency matrix.
No, it's not an alternative to the no. This is not an alternative to that. This is just saying here's some extra information. The extra information are these costs which we are telling you, and they're based on some parameter that's defined by whatever you're modeling in this case. Okay? Yeah, good question. Sorry for confusing you there. Okay. All right, so we know what the shortest paths are, right? The 1 to 4 to 7 to 6 happens to be the shortest in this case, right? Fewer or more nodes necessarily or more vertices than some of the other paths, but less cost altogether. Okay. Again, no path from, say, for instance, 6 to 1. You can go 1 to 6, but you can't go 6 to 1 in this graph. Not possible. Okay, not possible. Now, we can also do an unweighted path too, right? The shortest unweighted path, meaning all paths are just 1. They're all the same. The shortest unweighted path is actually 2 in this case, because you can go 1 to 4 to 6, or you can go, I guess that's it, 1 to 4 to 6, right? So V4 to V6 or V1 to 3 to 6, 1, 2, no, you can't. I goofed on that one too. Okay, so, but the point is that you can figure out what the unweighted path is as well. Okay? All right. You can have graphs that have negative weights. Okay? This tends to mess things up a little bit. Let's take a look at this. If you have negative weights or negative costs, right? If you wanted to go from 5 to 4, okay, what's the cost to go from 5 to 4? It's 1, because you can go straight there, right? Or you can go 5 to 4 to 2 to 5 again, and then back to 1, and guess what? The cost is -5. Right? Why? Because you're actually you're able to decrease the cost getting to certain vertices. Okay? This is not so good for figuring out our minimal path or the actual cost, right? We call that a negative cost cycle, and it means that you keep going all day and keep getting less and less and less and less and less, right? So it's not actually defined. The shortest path isn't even defined for this. Yeah.
What would be like a real-world example of
Let's see, a real-world example of a negative cost. Real-world example. Electrical engineering has some of these, where you have a battery, say, in a system, right? Where if you somehow set it up so that your battery's in the wrong place or whatever, you can actually you can have a current trying to flow in that direction continuously, and it would get more and more and more and more, and then your system would break. So things like that. There's probably a zillion other types of ideas. Yeah. But you can have this. And in terms of finding the shortest path, not going to happen in this case, because it's not defined, undefined. Okay. Other questions on this one? We won't be dealing with negative paths that often, or negative costs, or negative paths, or shortest paths with negative costs. Okay. All right. So let's look at some of these shortest path algorithms. In other words, how are we going to be able to algorithmically figure out the shortest path? Okay. We'll start with an unweighted graph, which, by the way, is just a special case of all weights are 1. Makes sense? Because you could make them all have 1 weight, and then you could do another algorithm. But let's just look at the shortest path from, in this case, vertex 3. We're going to look at vertex 3, shortest path to all of the other vertices. Okay, that's the idea here. Okay, we're going to pick vertex 3. And we're going to try to kind of figure out how we might do that. Okay. What we're going to do, this is kind of the basic algorithm here. Okay. Anybody want to think about what they might do for this? I mean, how you're going to start figuring this out? How you're going to go and figure out what the shortest path is algorithmically? Yeah. You could turn the adjacency list into a tree. It's not a bad idea. I hadn't thought about that. You probably could. The problem with this is this a tree, right? I mean, can you have certain cases that have, like in trees? What's one thing we never have in a tree, right? We never can go back up, right? We never have a child that has as a child its own parent. Right? It's a great book about that, about this, it's this really weird science fiction book about this guy who ends up going back in time such that and then getting a sex change such that he becomes his own parents. Really bizarre. Very, very bizarre, time travel book. But anyway, point is that you might be able to convert certain of these graphs into trees and do that, but it's not going to be every time, especially when you have cycles and things, because parents and children are not, in a tree structure. They're not a graph. Okay. Other ideas? How we might do this? It's okay if you don't. I mean, these are not easy things to think about. Yeah.
You could just find the lengths of all possible paths to get to the end.
You could certainly find the paths of all. You could start at vertex 3 and say, okay, I want to go to 1. What's all the different ways I could get there? Now you have to be a little careful about that, again, because you can get cycles, right? In this case, let's see. I guess in this case, it doesn't look like there actually are yes, there are. If you went 3 to 1 to 2 to 4 to 3 to 1 to 2 to 4 to 3 and kept doing that, right, you'd have to know when to stop. But you could probably do that. Okay. All right, good ideas. Let's just start going through how the actual algorithm works here. What we're going to do is we're going to say, OK, vertex 3 is our start position. And if we start on 3 and we want to get to 3, the cost to get there is 0. That makes sense, right? Because you're already there. There's no cost to get there. You're there. Okay. Well, then you can say, all right, let's look at all the vertices that I am adjacent to in the direction that I can go in, not the ones that come towards me, like towards vertex 3. It's the ones that it's pointing to. Okay, like 1 and 6. All right. Well, if you're starting at 0 and to get to 1 and 6 in a graph with no costs or weights, you're going to get to, it's going to be 1 to get to each one of those. Right? And then you just start, you can do this, doing it recursively is possible. Some you can do it iteratively as well, where you pick one of the ones you just went to and check which ones it goes to. Right? And you keep a list of which ones you've already been at and already dealt with. The ones you've already handled, you don't go and handle them again. In other words, you can if you go from 1 to 4 and then 4 back to 3, 3 is already done. It already has a cost of 0. And so you don't need to go back and deal with that. But anyway, you go to 1. And in this case, we have 1 goes to both 2 and 4. And therefore, if 1 is already 1 and it's 1 more to get to 2 and 4, then you add them together and you get 2. And both 2 and 4 have a distance of 2. Okay. And there aren't any paths from the other vertices in 1, so you don't have to worry about in 1, so you don't have to worry about that one. Okay. All right. Then we go to, let's see, did I skip 4? No, we did 4 as we can do 4 as well. No, you're then going to go to both 2. Let's see. You're going to go to distance of 3. Okay. All right. So the ones we've already had that have the shorter paths, we don't worry about. Okay. We go from 2, we get to 5, and we go from 4, we can also get to 5, right? It happens to be 3 in both cases. Or we can go from 4 to 7, and that's going to be a cost of 3. Okay. And in that case, and I guess we went from 4 to 6 as well. No, sorry, we didn't go to 4 to 6. You check 4 to 6. All right, so you check 4 to 6, and you say, all right, if I go from 4, which is 2 plus 1, that would be 3. Oh, look, 6 is already 1, so I'm not going to change it. Okay? And I haven't talked about how we're going to actually represent this yet. I'm just kind of going through the basic algorithm. This is a modified breadth first search. Remember when we were looking at level order in trees? We would do the first one level, and then the second level, and the third level, and so on. This is a modified way of doing that. Notice you start at you start at the start at vertex 3, and then you look at the ones it's pointing at, and then you go for each one of those and look at which ones those are pointing at, et cetera, et cetera. Okay, so it's a breadth first search in this case, similar to level order for trees. Okay. So here's how we actually here's how we might represent it in a table of some sort, right? We can have a table that looks like this. You've got all of your vertices down there. And then what you do is you say whether or not you have dealt with them yet, whether they are known or not. Okay? And you start out saying they're all false, for none of them are known at the beginning. Even 0 is not known at the beginning, although you do know its distance. Okay? And this is kind of how the algorithm progresses. And what you set for the distances for all the other ones that you don't know yet either, you set it to as big a number as you can. Infinity if you've got one in your programming language, or some really giant number that you're going to say is the maximum number. Okay? And you just keep the table, and you update the table as you go along. Okay? And you update the table when you have finished with one of the vertices. Okay? You say that you have now known that vertex, and you don't ever need to check it again. Okay? And that's kind of an important part. You don't actually need to check the ones that are already marked as known. Okay? because it's unweighted, as you check these, you just add 1 to the distance of the next ones that they're adjacent to, and you go along. And I'll walk through this step by step, showing you how this table gets updated. Okay? All right. Oh, first of all, I'll show you a little bit of that. You don't need to look at this right now. What this is basically doing is showing you a breadth-first search for this. Okay? This isn't the best way to do it in this iterative case here, basically because it is an n squared, a v squared in terms of the number of vertices algorithm, right? And it can actually be a really bad case for this because you go 1 to 2 to 3 to 4 to 5. You have to look at 1, then you look at 2, and then everybody else, and then 3, and everybody. It's not the best algorithm in the world. Okay? Don't stress about the details of this, but you can go and look at it kind of at your leisure. Okay? Here's how we would do it with the actual algorithm itself here. Okay? So we start with the vertex 3, which is our start, and we mark it as a distance of 0, but it's not actually known yet. Then you go and you do this algorithm where you say, OK, now I'm going to go to its adjacent vertices. Now I'm going to mark vertex 3 as known. And then I'm going to add 1 to my distances for the ones that are adjacent to me. Okay? Then you do the same thing. You go to 1. And it doesn't actually matter in this case which one you go to next. It will come out the same with the same distances, minimum distances anyway. Okay? And you go to 1 and you say, OK, now I'm going to have the vertex 2 and vertex 4. And I'm going to those. And I'm going to now say that vertex 1 is known. And vertex 2 and 4 have the cost of 2. Okay, you see how this is kind of building up? Okay, same thing. You go to 6. 6 doesn't have any, so you don't have to do anything. Okay, you mark it as known, and that's it. Okay, then you go to 5, and it is 5 goes to 7, and sorry, for 2, you actually only you go to 5, you check 5, and 4 is already known to you, so you don't even need to bother checking 4. So you go to 5, and that's going to be 3. And then you finally go to, let's see, did I skip 5? No, I think I might have. Oh, no, 5 is already, I think I might have skipped 5. And then you go to 7, and you update 7 to 3. And then everybody, oh, no, 5, we haven't gotten to 5 yet because 4 updated 7. OK. And then we go to 5. And 5, because, let's see, you go to 7, it's already known. And you then, oops, and then you finally are everybody's known. And that's that. OK, so you can walk through this algorithm kind of on your own. But that's the bottom line here. OK, can we do better than n squared? You can. Remember how we did the level order traversal for trees? Do you remember what structure we used for that? It was a queue, right? If you do the exact same thing for this in terms of putting things into a queue, and I'll show you the code for this, what it actually does, it's basically enqueue the first start node, or start vertex, okay, and then go through and dequeue it, and then enqueue its adjacent vertices, and then check them in that order, first in, first out. And you will actually not have to walk through the entire, you won't have to check the ones that are already known to you, as it turns out. There may be a case where you go and there may be a case where you can't get to some vertex from the start. This might be the case you can do that. They will be represented as infinity, which makes sense. Right? If you can't get there, it's going to have a cost of infinity. Can't get there. Okay? All right. Questions on that? Anything else? All right. I'm going to stop here because in 5 minutes I don't want to cover this whole topic in 5 minutes. The next big algorithm is going to be this thing called Dijkstra's algorithm, which is exactly what we were doing for the unweighted paths, except now for weighted paths. This is actually one of the most famous algorithms and used all the time, and it's one that we should spend a little bit more time on than 5 minutes. Other questions? Yes. I'm sorry. What was the capacity of what? The complexity with the queue, yeah. The complexity with the queue is, I didn't write it down. I believe it is it's log, but it's based on the number of vertices plus the number of edges, I believe. I'll look it up. I'll get back to you on that. I'm not exactly sure. Yeah. Okay. Other questions? Yes. Avita? Would a linked list be considered a graph? Sure. It would be considered not a very interesting one, but sure, it could be considered a graph. No, I mean, you can have a linear graph. It's just they're not linear in general. Like in the general case, they're not linear. Yeah. Yes, a node that points to itself is also considered a graph. You have to be able to deal with those when you're doing some of these algorithms. Yep. Yep. Good. Anybody else? All right. See you on Monday.